Howdy. We are at Zurich Insurances. And I just stumbled across this. I haven't read it until the end, but it seems very interesting. Since we are talking about what is space weather and how does it affect us down on Earth? And that's a week old or something. On Earth, severe weather is cause for major concern, but up in space, solar winds and geomagnetic storms can be just as devastating as we increase our reliance on in orbit infrastructure. Is there anything we can do to prepare us for this? Yeah, make the chimney. Space has never been more important to us down on Earth. Earth is in space, so it has always been important. Around 11,000 satellites have been launched since Sputnik 1 in 1957, as many as 7,000 more could be put into orbit over the coming decades. This space infrastructure supports a number of vital systems such as broadband, GPS service, climate monitoring, financial transactions, timing, and crucial military technologies. In other words, many of the services on earthbound societies have come to heavily rely on are now speeding around our planet in space. But as we move critical infrastructure to space, we are exposing it to the risks of space weather. Space weather relates to the magnetic fields, radiation, particles, and matter that are ejected from the sun. They interact with Earth's upper atmosphere and surrounding magnetic field to produce a variety of effects. The most recognizable space weather effects is the auroras, the northern and southern lights. But some effects can cause extensive damage, including solar winds and geomagnetic storms. For instance, in February 2022, SpaceX, owned by billionaire Elon Musk, lost 40 satellites after they were hit by a geomagnetic storm a day after launch, causing them to fall from orbit and burn up. What is a geomagnetic storm? The geomagnetic storm is a major temporary disturbance of Earth's magnetosphere caused by a strong surge of solar wind called coronal mass ejection. This generates electric currents in the near-Earth space environment. Apart from radiation damage, satellites can suffer from significant drag as a result of solar activity. This is due to the effect of celestial particles have on the density and temperature of our atmosphere. After a solar storm, the North American Aerospace Defense Command, NORAD, has to readjust the trajectories and orbits of hundreds of objects to avoid collisions. The biggest geomagnetic storm in the 20th century hit Earth on March 1989. Satellite operations were crippled. Several objects were temporarily lost in orbit. When NASA's Solar Maximum mission spacecraft dropped as if it hit a brick wall as a result of increasing drag. It even caused a complete blackout in Quebec, Canada, and hindered electricity transmission in the US, the UK, and Sweden. What is the solar wind? The solar wind is a continuous stream of charged particles emitted by the sun. It is deflected by Earth's magnetic shield, causing most of the solar wind's particles to flow around the planet. The solar wind is visible in the halo around the sun during an eclipse and sometimes when the particles hit Earth's atmosphere as the aurora borealis, northern lights, or Australia's southern lights. The socio-economic impact of similar geomagnetic storms is difficult to estimate with precision. Some reports state damage could be contained and repaired relatively easily, while others predict a doomsday scenario of worldwide power outages lasting weeks or even months. It's for this reason that the UK added the risk of severe space weather as a medium to high likelihood scenario to its national risk assessment in 2011. On a practical level, it isn't hard to imagine that GPS disruption of even a few microseconds could cause a cascade of failures in electrical grids, phone networks, stock markets, healthcare, air travel, and other systems all at once. This is already a central consideration of anti-terrorism strategies. So it is no surprise that in 2016, President Obama issued an executive order to prepare key US infrastructure for extreme space weather. This includes setting up reliable backup networks and enhancing monitoring capabilities. Many countries have since followed suit. Space weather's impact on climate change. There is also concern that space weather, with its fluctuation density and temperatures in the atmosphere, could have a long-term impact on Earth's weather. Really? Yes, it does. Combustion emissions from rocket engines are already having an effect on our climate. Solid rocket engines not only eject dangerous substances like chlorine directly into the ozone layer, they also release particles into the atmosphere that impact the solar energy and change the flow of radiation, heating the stratosphere, cooling the surface, and depleting the atmosphere. But they are so minor, there is no. Like, maybe few hours it could do something, but then it's gone. As the space industry continues to grow with ambitious plans, it is important to acknowledge we are making ourselves not just too vulnerable to space weather, but to on-Earth weather changes as well. Changing jet stream patterns are related to magnetic pole shift or excursion and weakening magnetic field of Earth, which those are going on simultaneously. So there is more energy coming in. The jet stream patterns will change because the position of the Berkland currents are changing too. And we are dealing with the what are they? Diachron instabilities. Yes. Anyway, assessing and managing the risks. The most intense geomagnetic storms in recorded history occurred in 1859 and are known as the Carrington event. It created auroral displays observed across the globe and caused telegraph systems to spark and catch fire in Europe and North America. But we should not assume this will be a one-off event. Carbon-14 isotope data from three rings indicate that the Carrington event also occurred in 774 BC and that similar-sized events happen every several millennia. 6,000 and 12,000 years are the biggest ones. But anyway, smaller events such as the 1989 geomagnetic storm that caused the power outages in Quebec also happened in 1921 and 1960. A Carrington class strength storm did erupt from the sun in 2012, but fortunately narrowly missed Earth. After that event, researchers from Lloyd's of London and the Atmospheric and Environmental Research Agency estimated that a Carrington class event impacting Earth today would cause damages totaling of US dollar 0.6 to 2.6 trillion dollars to the US alone and cause widespread, if not global, electrical disruptions, blackouts, and damages to electrical grids. The impacts could be long-lasting and power restoration estimates range anywhere from a week to the least affected areas to more than a year to the hardest hit regions. Television signals from satellites would be disrupted significantly, and satellites too would experience disruptions to radio frequency communication, crippling GPS navigation. A deep understanding of space and the forces that shape it will be needed to effectively predict the events that could critically wound our vital tech systems. In parallel with forecasting, there is the route of infrastructure hardening, an expensive and laborious process. Both routes will require significant investment to ensure computer models, protocols, and skilled staff are on hand to predict and react to space weather. Thorough risk assessments will need to be conducted to identify vulnerabilities and prepare appropriately. But increasingly it seems like a wise investment. So I suggest to everyone, watch at least this video and all the others relating to the same theme. Not only from Donald Scott, which is presenting Ralph Jurgen's electric sun model. Let's have a quick listen. And this is from 2016, and the electric sun is much older. So the knowledge would be there already.
Lastly, in the central curve there, the electric field curve, you'll see there's some blue areas and some salmon-colored areas. This is strictly from Maxwell's equations. If you're going to have an increasing electric field, doesn't make any difference what the sign of the electric field is. If it's negative or positive, makes no difference. If the electric field is increasing, you're in a region of plus charge. And you can see that's what happens there right next to the vertical axis in the middle plot. So that's the positive charge layer. Where the photosphere, the voltage is not changing, there is no electric field, so there is no charge.
So, one thing to end this video I wanted to show you. For this we go over to NASA Spaceweather Live application. We want to find out solar activity. Then we go down to solar cycle. Solar cycle progression. Solar cycle 23, 24, 25. We are here in solar cycle 25. And there are those who are predicting, or who were predicting about this grand solar minimum. But we are still quite some distance away from the peak of our solar cycle, but we are already up here. Compared to the other solar cycles, we are not exactly, but almost at the same level as solar cycle 23 was peaking, and it had a double spike. So it might be, or is really interesting to follow that, how high this line still continues. Since it's very steep, and we have still way to go in this direction, this might rise still to some extent until it goes down. So we have to be prepared for 2 years still it's rising. Approximately. So the influence of solar activity, Earth's magnetic weakening fields, this is very important, and now even insurances are talking about this. Yes, very interesting. Thank you. Bye.